My name is Hendrik. I work for Missing Link Electronics. And maybe a quick word about my background. I did my PhD in CAD, which nowadays is called Electronic Design Automation. So I'm a software engineer by training. And my first exposure to TCP was in probably 1990, 91, when we used TCP socket interface to write basically bots for NetTrek. Anybody remember NetTrek, which was kind of a multi-user online third-person shooter game in space? So here I am giving a presentation on how bad is TCP, despite the fact I spent countless of fun hours in front of a Sun workstation hacking TCP, okay? But the title is not really my invention. That was an invention, or that was the question we got asked by one of the CTOs of a tier 2 data center company who we were pitching on some other improvements, some other protocols, and he said, Hendrik, how bad is TCP? Because at his position, he didn't think it was any bad at all, okay? So what we're doing is we're going to look at TCP and some of the behaviors of TCP, which we all take for granted, but some of the behaviors of TCP or some of the functionality of TCP is probably not suitable in the modern world of distributed systems, okay? And that's basically what we do. We build distributed systems, systems of systems. We sometimes refer to this as high-performance embedded computing. And that's why every now and then I show up at SDC, because I get inspiration and technologies and tips and tricks from some of the HPC guys and some of the data center guys on how to build certain systems in the embedded world, right? Where we don't have that many CPUs, where we have other environmental challenges, shake, rattle, roll, heat, temperature, humidity, but at the same time we need to be computationally very, very efficient, right? And what we really do is we're FPGA company, so we use FPGAs as affordable silicon to turn software algorithms, protocols into silicon, mostly to offload CPU. And the idea behind that is A, get better performance, B, lower and deterministic latency, and obviously improved energy efficiency. And the areas that we basically work on is these kind of connected embedded systems where we do vehicle-to-vehicle communication using 6G radio. 6G is a new development. We're using side channel, or side link it's called, for vehicle-to-vehicle, drone-to-drone communication, but we need real-time aspects behind that. We need reliability, we need security, but we also need real-time aspects of that. Another field that we're working on is these modern zone-based in-vehicle networks, topic that I think we presented here at SDC a few years ago. Key driver behind that is that in these modern cars, we end up with a wire harness that connects 99 individual computers together. The wire harness these days is the second most costly component, and you would imagine that this would be good business for the guy who sells the wire harness. No, these guys are selling it at a loss, and then you know it becomes an engineering topic, because you got to do something better than that. And the third thing is we're doing a lot in factory automation, virtualization, microservices, virtualized programmable logic controllers have hit the industry floor, the factory floor. And with the advent of AI and high data rate sensors, there's a tsunami pushing away these old standards, Profibus, Circos, I mean, there's a language and standard soup in this world, towards high bandwidth, reliable, secure, real-time communication. And that's basically the topic that we work on at Missing Link Electronics. And our work motivation is basically implementing systems of systems, right, where these systems are tightly coupled. where we use distributed processing because we can't get energy or cost-efficient individual computers to just deliver the performance, so we have to scale out, similar to what has happened in data center. And we see microservices creeping into the automotive, the embedded, and the factory automation floor, similar to Dockerization or containerization in Linux these days. And at the same time, they're loosely connected. And with loosely, I mean, they're not really connected with super high bandwidth PCI Express, CXL. They're connected via network, right? And the network, we all understand, is becoming a bottleneck again. And that was actually the motivation for us looking into other protocols. At Missing Link Electronics, we're pretty much agnostic to the physical layer, and we look at protocol layers, layer 2 and higher application layer for optimizations. And the optimizations we do is first and foremost power and energy efficiency. Well, like the cost of a watt per year in a data center tends to be like $2 to $5 depending on geolocation, but this can be worse in an embedded environment, in particular when you are running on a battery alone, right? Everybody understands a drone for delivery of goods is utterly useless if it can only be a minute in the air, right? So energy is something you need to be very efficient with, and in particular computation tends to burn a lot of energy these days, and that's what we're trying to optimize as well. And the other thing is throughput. One of the things that we see is more and more trend towards high bandwidth, high data rate sensors. What used to be a proximity sensor in automation and or an ultrasound sensor in the car industry is now radar, is a LiDAR, it's MIMO radar. Okay, that's very quickly tens of gigabits of data that's been spewed out by these sensors, and somebody has to transport it, and some processing elements have to digest and process that data. And the other aspect is deterministic, low latency, and real-time delivery, right? Nobody wants an anti-lock brake and you hit the brake pedal and the system engages eventually, okay? Very obvious example, but in order to build this stable system of systems, we need very deterministic latency. We need to translate into worst-case execution time, worst-case transport time, in order to schedule the behavior of such a distributed system. And what we basically do is we build these domain-specific architectures. Again, make heavy use of FPGAs wherever we get them from these days. And we offload protocols and or algorithms from software, typically open source software, into silicon. But unlike others who kind of invent their own proprietary protocols, their own proprietary standards, we're a strong believer in open standards. IEEE Ethernet, IEEE TSN stands for time-sensitive networking, open source Linux. That's basically the standards and interfaces and APIs we adhere to, and which we are accelerating using offload engines. And what we're really looking for is the new world of high bandwidth, secure, real-time networks for communicating and connecting systems of systems. And these systems today, pretty much like in the data center world, they use a lot of TCP, okay? TCP, TCP IP. And the idea behind that is TCP is a reliable protocol. You can hire anybody out of any engineering school. He probably has a good understanding of TCP, if not even had classes, lectures on TCP, right? And what we're doing is, because we're accelerating things, we're offloading things in an embedded environment. Our interest is the computational burden of TCP. That was the first and foremost interest, because unlike in data center where you have quad socket, multi-gigahertz CPUs, we sometimes have to deal with a 32-bit ARM CPU which runs at 700 megahertz, okay? And we have applications which all of a sudden need to drive gigabits of data over TCP. So all of a sudden we bumped into a wall, we bumped into the computational burden of TCP, and we have some data to share with you guys, mostly on TCP costs, running TCP in modern Linux systems. And the other thing that interests us is how good is a real-time network, a TSN network, if on top of that you run a protocol such as TCP, which can have huge tail-end latencies, okay? And that's why we reached out and looked at who's working on alternatives, and we bumped into John Ousterhout at Stanford University and his invention, so to say, the Homa protocol. And that's basically the second topic of my talk, presenting to you the concepts of Homa, the protocol, and the benefits it may not only have in embedded systems, but also in data center. John's work is basically focused on data center. And in particular, I'm closing this one with a slide looking at how can this new protocol be used for NVMe over Fabric. And that's basically a request for discussion after my presentation or at this show. So let's look at some of the functions of TCP. And I mean, like, we're all aware of it, but and it's subconscious, but let's visualize some of the aspects, okay? TCP is a byte stream, okay? If I want to transport the video, that's fantastic. One frame after the other, it's a big streaming thing. But most distributed systems are message-based. They have remote procedure calls. They have sometimes rather short messages, an acknowledgement or a quick request for more data or synchronizations, right? And if you look at these messages here, kind of visualized on the left-hand side, they come from many different spots, many different pieces of software in the system. And if you transport that over TCP, you lump it into one big TCP stream. And because of TCP segmentation, the receiver is now burdened with taking these chunks of a stream and turning it back into messages, okay? So that's basically the first downside of where we see TCP is not the best protocol. It does have some fantastic features, but if you start to transport messages, it's not really good. You add complexity, you add overhead just for the message reassembly alone. The other aspect is load balancing. I mean, like in the data center, we're used to it by now, but in embedded computing, we need to run on multi-core systems. We need to do certain load balancing, and in particular in a mildly distributed system as well, right? So if I end up having these messages chunked in TCP segments, okay, I can't put the individual message on a worker thread, on a worker core, because it's a stream, okay? And that adds to the problem set of TCP, where you can't really share one stream over multiple threads and then have one thread work on, let's say, the green message and the other thread work on the orange message, for example, okay? That's very, very difficult. And the other side effect is it's very difficult for network interface cards to do some smart offloading and handling at message level, right? Because there's no way to dispatch this one stream in form of multiple messages over to a NIC for doing certain types of offloading. So what do? We basically see two approaches. Choice number one is you have a dispatcher thread, right? You receive the one stream and you dispatch the stream with individual messages to these worker threads. And that basically has a downside. It creates extra latency for the send-off between the dispatcher and the worker. And the second thing is this dispatcher very quickly becomes the bottleneck for the network throughput, up to the point where you can estimate about 1 million messages per second and you quickly saturate that dispatcher node or core. So the alternative that we see a lot in embedded systems is you partition the connections. Instead of having this one TCP stream, you have a couple of dozen TCP streams. And you do what we call static load balancing, right? Where one TCP stream gets handled by one CPU core, it's fixed by interrupt affinity or CPU affinity, and that is nice in the sense of it shares the load, but Sometimes it puts the load just on one CPU core, there's no dynamic handling, and you basically end up with hotspots in processing. So let's look at another aspect of what happens when you aggregate individual messages into a byte stream, okay? And basically it means head of line blocking. So in order to get to this, let's call it super urgent orange little message, okay? The recipient needs to receive the green message and the blue message in order to get to the orange message, right? It's just a way of stream processing, okay? And that leads to one of the aspects that we don't like at all in distributed systems, very high and sometimes very non-deterministic tail-end latencies. Up to the point where we looked at 5G, they call it ultra reliable, low latency communication for factory automation campus networks. And we see sometimes 25 milliseconds of tail end latency for some of these very short messages because it's TCP based. So the other aspect of stream level reliability, where stream level reliability is actually inadequate, is TCP timeouts, right? TCP was done from basically the original idea was to have one node communicate with another node, and you knew the nodes would be there, and there could be a timeout in the transport, and that was it. But in a massively parallel system, in a distributed system, it's very difficult. In particular, if you deal with messages where all you say, well, my message is a quick request, please give me this thing, and you expect a response, okay, and then you want to make sure that your request has been processed, and eventually you get a response, and you basically need to deliver the response reliably. If there is an error, okay, you get notification. That's what you expect. In TCP, it's a timeout. It's a retransmit or timeout. And that's definitely not helping in order to have bounded latency and or put a cap on deterministic latency. Stream guarantees. That's actually weaker than what we need in message-based systems, right? We have a best effort delivery of the request or the response. It ends up as a byte stream on either side, but there's not really notification that a server crashes in the data center. Or in our case, you got a physical damage or a single event upset in one of those compute nodes in your embedded system. Okay, that's why you expect a different handling at reliability level, and that's why we believe that clients should not implement their own additional timeout handling at application level. It should be part of the protocol, okay? Even though TCP has these timeouts, we don't think it's appropriate for building reliable distributed systems. So the other aspect is TCP is connection oriented. So the first thing that we notice is you gotta keep these long-lived state information around, which in the embedded system is just an extra burden. But in data center, where you can have millions and millions of those connections alive, it starts eating into your RAM, right? You have to keep the state separate. You have to keep it to some degree persistent, even if you got a power outage at some nodes, okay? What makes this hard, keeping this state persistent, is if you start offloading TCP in a NIC, particularly an FPGA-based NIC, you got to keep all those connections alive. And one of the most precious memories that we have in these smart NICs, in these FPGA-based smart NICs, is memory, right? DRAM is rather slow compared to the line rate of processing in an FPGA. Embedded block RAM is a very scarce resource. We still count it in megabits, not in gigabytes, okay? So that's a downside of having a connection-based protocol where you need to keep the connection state alive for a while. The other aspect is, in order to send some data, you need to establish a connection first. And that basically suffers from a round trip time, right? You send the SYN, you get the SYNAC, and eventually, okay, now we have a connection, now give me the data. Just give me the data, Okay, send me the message. That's the idea. And if you have a serverless environment with microservices, right, sometimes you just want to send short synchronization messages around, and you will never ever be able to amortize for the huge round trip time for establishing the connection. Okay, and that's a problem for building these distributed systems. The motivation for connections obviously was enable reliable delivery, right? Make sure we have a connection established, we understand we are talking to each other, I'm expecting data from you, okay, I'll acknowledge the data, and then you know I received the data. We have flow control, we have congestion control because we share a shared medium for communication and so forth. But the truth is, you can have that reliability, you can have that flow control, you can have that congestion control without having connections, just in a message-based approach. Third topic, TCP is known to use fair scheduling, okay? But what kind of a fairness is it if every single connection or every single message suffers from the same latency, right? So read this chart as this is a time, and you basically get your message by fair scheduling, you chop it up, and at the end of the day, all these three messages are delivered, and that's when you can start computing. Why not have the blue one do this, so at least this one is in favor of an early completion, then have the green one, and the orange one, nothing really suffers. The orange one isn't much later than before, okay, but the green one and the blue one is arriving or is received much, much sooner than in a fair scheduling approach, okay? And it's kind of the concept of, well, fair scheduling, everybody finishes poorly as fair, okay? That's probably not the good approach in order to build these efficient distributed systems. And there are other approaches now known. We call them run-to-completion approaches, or SRPT, which are far better. And the protocol, Homa protocol, that we're proposing here basically works on this. And that basically means you need to understand the message size. That's inherent, obviously, in the Homa protocol, and all of a sudden you know when the message will be delivered and received and processed. And actually, so this is data from one of John's PhD students, where they basically looked at how fair data gets transported. And let me explain this chart to you, because it took me a minute or two before I first understood it. Y-axis is what they call the slowdown. That is the time it took on an unloaded network, just with this exclusive connection, versus the time it took over a loaded network. And in this case, it's kind of a generic workload according to some network benchmarks. And in this case, the network is 80% loaded. And this data, this simulation data, was basically done with 100 gigabit Ethernet underneath, okay? And the x-axis is the message size, okay? And the green one is for TCP P99. P99 stands for the 99th percentile. That means the 1% really bad or worst latencies that we receive are cut off. We just look at the 99th percentile. And the brown curve, which is slightly better, is datacenter TCP, which is a flavor of TCP. So what you see is basically these small and short messages, okay, which suffer through a slowdown of 100x, okay, are not really treated in favor. Large messages, like 1 megabyte, they have a much better slowdown, okay? And basically there's, in this chart, there's a 9x, almost 10x bias for these large messages and disfavoring these short messages, right? And I don't think this is a proper approach to fairness in a distributed system, where it's just like shortest job first, get this thing done, get it out of the way, and then the communication can continue. Last aspect why TCP may not be beneficial in all those cases anymore is sender-driven congestion control, right? The sender is receiving X or not receiving X and then scaling down the transmission based on congestion or based on packet overflow or buffer overflow, okay? So the sender doesn't really have an understanding of the workload it's generating on the receiver end. And it's a pretty blind approach as we see that. And what we do see is now kind of band-aids on TCP, where we use quality of service, multiple streams. We use TSN or flavors of TSN for packet prioritization, just in order to handle those kind of aspects of congestion control. The other aspects we see in data center network is packets get dropped when the buffers, the queues overflow, right? Quite frankly, we try to have very short queues because queue length adds to the overall transport latency. But if the queue is too short, you lose too many packets. That has other negative side effects, right? So that basically ends up in a catch-22 where you want to keep your buffers as short as and as shallow as you can in order to favor low latency. But at the same time, you're risking of losing too many packets, which triggers a retransmit, and that makes overall latency even worse. So the other aspect that we see is the pure computational burden of TCP. So we're one of the guys who put TCP into a digital circuit. It's basically technology that we licensed from German Fraunhofer in Berlin. So we get these repeat calls from users, engineers who run maybe an 800 megahertz ARM A9, okay? They have a 10 gigabit Ethernet port, and they expect 10 gigabit of TCP transport, okay? And they're dead lucky if they get 2.5 gigabits, okay? Just line rate. And that basically means TCP has a significant compute burden. So one of the things that we did is we just took some generic machines in a virtualized environment, and we rule out that virtualization is any performance issue because we do PCI Express pass-through of the network interface card, so very, very little performance is lost in this one. And we run NetPerf as a benchmark suite. There are many other things, QPerf, iPerf, they're almost the same. We like NetPerf because it gives us a stream where you have the bandwidth computed from a sender to a receiver. It gets a merge where basically go the opposite direction. And the setups we're using is in order to test and validate not only the computational burden, but also the latency, is where we have two servers running various flavors of Linux. You can see this here with multiple colors inside, either talking TCP with each other, or we have an FPGA-based implementation. To those who know the acronym, ZZU is one of these AMD development kits with FPGAs inside. And that allows us to do Linux to Linux, or FPGA to Linux, or Linux to FPGA, or FPGA to FPGA. It means full acceleration in the path, okay? The results I'm showing here is for a 25 gigabit Ethernet connection in between, because that's where we see most of the interest in the embedded world. And they're not at 400 gigabits at all. That's way too expensive for them. And the fun part is we see huge differences over the various Linux kernel versions. Not so much in the distributions, but over the various Linux kernel versions. And it's actually where my colleagues in engineering are quite interested. Anybody has a clue why this might be the case? We're very interested in understanding this. So here's the first result. This is a TCP stream result where you can see the theoretical bandwidth with basically these X's. Okay, obviously for small packets like 100 byte sized packets, the protocol overhead of TCP, which is about 64 bytes, is significant. So even in a 25 gigabit network, you can achieve barely 15 gigabits. Okay, that's kind of that curve. Okay, And the other thing is, in this case, we have 3 flavors of Linux kernel versions, 636, which we downloaded from kernel.org, 515, which basically is the default for the Ubuntu 22.04 long-term support distribution, and 419, which is also a precompiled package from kernel.org, okay? And what you basically see is a couple of things. First of all, small messages, 25 gig networking, you're far away from making line rate because the computational burden of TCP is hogging these CPUs, okay? The other aspect, eventually you close up to the line rate of the underlying Ethernet, but you see these odd things. Like the blue one is for the kernel 515, and we are still digging into the kernel and in some of the documentation, trying to figure out why there is such a huge spread between the best bandwidth or throughput versus the worst throughput here. Okay. The other aspect is CPU load. The way NetPerf shows us the CPU load is in percentage of all the CPU cores. So this was a 4-core system, so 100% translates to all 4 cores are fully loaded. And what you basically see here, it's on the transmit side of the TCP Linux, on the left-hand side the transmitter, right-hand side the receiver. We constantly hog 1 CPU core until eventually the message sizes gets a little larger, and then obviously the handling gets a little less burden. And quite interesting, a very old Linux kernel 419, okay, seems to have less CPU load despite all these optimizations that went into the Linux kernel for handling TCP. On the receiving end, you basically see the opposite effect, right? For higher data rates or larger message sizes, you create additional burden. And that seems to be related to the fact that the modern Linux kernels, they now do receive offloading, GRO, general receive offloading, and they basically have another thread or another processing element for basically taking the payload and then have another core work on this one, okay? And that's creating another significant burden in processing. And again, these were Xeon E1620 CPUs, not top of the line, but we believe they're representative in terms of compute load. So for our embedded customers, we created this artificial figure of merit or metric, which we call efficiency. And efficiency is gigabits per CPU core, all right? And what you basically see is if you're now using TCP in a distributed environment and your message size is rather small, okay, you're highly inefficient. Again, TCP, stream-based, does very well for large message sizes or large byte streams, okay? And we see some interesting effects for the old kernel 419, where all of a sudden the efficiency seems to be much higher for larger messages than for other Linux kernel versions. Same thing here on the receiving side, okay? So takeaway is TCP is a protocol which creates quite some burden on modern CPUs. Here's round-trip results. So NetPerf benchmark can report back to you the round-trip time, and this is again between 2 Linux machines with their NIC, PCI Express, pass-through, and there's a simple, I think it's 100 gig Arista switch in between. There's not much more in between, okay? And what we basically see is that there's about 20 to 25 microseconds is spent in the software system for handling the TCP IP protocol, making it ready to be sent out and making it ready to be received, handled, and then the response comes back. Okay, and quite frankly, many years ago, I went to SDC, and somebody pitched NVM Express, okay, over SATA and SAS, and basically said software considered harmful. That was, I think, a pitch from UC San Diego or UC Riverside. Okay, we said, we got to get rid of these legacy protocols in storage. So that's what we basically did. We didn't get rid of the TCP IP protocol, but we put it into a digital circuit. And I have some details on that particular implementation. And that's what you see. If you do this in a digital circuit, then basically the clock rate, in our case of the FPGA, it's about 300 megahertz, is directly influential of the round trip time, okay, plus the cable length and the speed of light, which to some degree is negligible over clock rates here. And what you basically see is this is highly linear with message size. That's kind of what you're expecting as well. But processing TCP in a digital circuit can be rather fast, and the data that we see is less than a microsecond for processing a TCP packet, a 100-byte packet, if you do this in a digital circuit, compared to 20 microseconds if you do it on a CPU and software. So let's look at alternatives. Okay, now as we understand some of the deficiencies of TCP, let's look into the Homa protocol from Stanford University and figure out whether this is suitable for some of your applications, and we're highly interested in engaging with you guys to see whether there's something that we oversee or something that you see in this protocol that we should further investigate. So the first thing is, within the Homa protocol, there's explicit information about the dispatch units, like from who sends to whom. That gives us one cool thing in software, because you can have multiple threads, multiple message threads, okay, be handled by one and the same socket, okay, because the message has its information from whom to whom, okay. And that basically means you can use a single socket, which makes it a bit easier for maintaining or implementing software APIs. And what's even more interesting to us as folks who love to accelerate protocols is it makes it easy to dispatch those messages within a NIC, within an FPGA-based NIC. The other aspect that Homa implements, it implements the run to completion concept, SRPT, right? That means shortest job first, get it out, and don't append it to a stream of other messages. Homa is connectionless. That means in order to send data around between, or for a remote procedure call, for example, okay, there's a request of the message, there's a response message, okay, and the remote procedure calls themselves are completely independent. They're not eating from the same TCP byte stream and need to take care of sharing this information and then basically partition it off. Next aspect is, because it's message-based, there is no long-lived connection state. Yes, there's state information in there, okay, and our analysis based on John Ousterhout's open source implementation is it's about 200 bytes. But 200 bytes is something which is, in a short-lived message environment, by far more digestible and much more suitable for hardware implementation than having 2 kilobytes for tens of thousands of connections, okay? The thing that we like a lot is there's no connection setup cost, okay? There's no overhead. In order to send a request response, the sender sends a request, recipient responds, and there's actually a concept called RTT time, where short messages just get sent out, unscheduled, no questions asked, because how good is it to load the network in order to, well, here's a connection, here's it goes back, you got this extra load on the network adding to the round trip time, so just send me the data, okay? Highly efficient. And that basically allows to have one socket communicate with many peers at the same time, because you're not dealing with scheduling, just sending these things out. And what Homa also does, it ensures end-to-end remote procedure call reliability, right? There's no need for application-level timers like timeouts in TCP. There's no stream disconnects. There is a concept, obviously, for resending requests or resending responses. Okay, that adds to the reliability, but it's basically implemented by the semantics of the sender and or the receiver. The congestion control in Homa is receiver-driven. And the rationale behind this one is the receivers tend to get data from many different senders. In our embedded world, that's multiple sensor data, and the receiver kind of has an understanding how much of this data it can digest and process, okay? And there's another aspect for that, that's kind of these brown or orange packets, is these are unscheduled. So these short messages, in order to begin a communication, they're just sent out. No questions asked, just send them out, okay? Because everything else would be overhead to the network, which we all know is a bottleneck by now, and it's kind of a waste of time in order to establish a connection. Just send the data out. And then if the message is larger than these unscheduled for RTT time, the receiver basically gives grants. And in PCI Express, it's kind of credits, right? Flow control credits. And sends those credits or grants back to the sender, and then the sender understands how much the recipient is willing to receive. And that means congestion control is now handled by the receiver, which is to some degree favorable in a data center approach where the recipient sits in a server, microserver underneath a top of rack switch, and in an embedded system where the recipient normally becomes quickly the bottleneck for processing massive sensor data. In a data center, now we can reduce the congestion in the top of rack switches, okay, and most importantly, we can prioritize for shorter messages, and I have a slide on this one. The other thing is that the message size that basically the sender initially sends to the recipient allows the receiver to predict what will happen in the future, okay? If I'm about to receive a monster large message, then the receiver, the recipient, can basically do certain metrics and say, well, how about I leave enough room for the shorthand messages which are time critical, or well, scheduling, that needs to be done by another core, by another microservice, okay? So it allows us to look into the future from a recipient's perspective, while in TCP, the sender just keeps sending this as an endless byte stream until eventually the connection is teared down. One of the things that Homa does, and these are the subtleties for data center, and that's basically John's work of expertise, is using the sometimes 8 to 16 priority queues in these modern switches, right? The Ethernet protocol has priority tags involved, and the idea and the research that John and his team did was, well, let's use this to prioritize for short messages. The idea is basically you have a bunch of short messages, priority 0 is the highest priority, just get it out, okay? And then they learned that it was a bit inefficient, and one of his studies basically shows, well, you do overcommitment, right? Kind of what the airline industry does these days. They book a seat more than once, okay? And that overcommitment turns out to be very, very efficient, and it does not hurt the delay or the round trip time, the latency of these short messages at all, okay? It makes very efficient use of network even when the network is highly loaded, 80–90%. So here's the chart again of comparing the slowdown of TCP and or data center TCP versus Homa. And the first thing we notice is that these short messages, when you compare it of an unloaded network versus an 80% loaded network, it's only 9x worse. So there's a more than 10x improvement for the time to receive these short messages in a loaded network. okay? And the other aspect, if you look, is even large messages, okay, megabytes or larger, they're handled better than in the TCP case, okay? So that's a bit more of a fair scheduling or handling or use of the precious network resources that we think. And it's been basically done by a combination of receiver-based congestion control, where you use grants and you use priorities in the switches, where the run to completion concept, rather than a big fat byte stream, improves the performance for every message, not just the large ones, but in particular the short ones, which we need for synchronization of processor nodes, okay? And there's very little starvation risk for these very long messages, and that's also something we see, because in our typical embedded systems we have to deal with these camera streams at the same time when we have synchronization messages, just short synchronization messages like, well, engage the brake pads, for example.
Question about that, Brad. Was that based on a simulation?
Yes. Yes. I have a list of these references, and I'm more than happy to go into the details as much as I can. I'm still learning from John and his idea. But these are simulation based, and he has a ton of these different workloads that he compared. And I think these were even public workloads kind of published by Google. So the other aspect is, for those messaging, there's no order requirements, right? In TCP, a stream, there's a packet order. And if you do packet spraying over data center network, or in our embedded world, we call that rerouting, right? We sometimes have torus rings, because if you have a fender bender on one side, you don't want to break your entire backbone of your car. Right? You have to have some kind of redundancy, and massive redundancy is in data center network. So packet spraying is basically nicely facilitated, because the recipient, he gets just the messages, no matter how they were sent through the network. And so, well, it's a stream, I need to reorder the stream, and then I need to dissect the stream and get my messages out of that stream. Okay? And that also leads to much better CPU core load balancing that we see. So one of the first things that we did when we jumped onto this Homa protocol, about a year ago we engaged with John, was every engineer, in order to understand a new thing, needs a debugger, right? So what we did is basically we implemented a Wireshark dissector, put it onto GitHub, where it's now a helper tool for us and anybody who's interested in learning more about Homa, because it shows the different Homa messages, and that is important to us. And I can share the link. The link is in the slide. It's kind of hard to read. Second aspect is we're really looking at Homa for implementing this into what we call our network protocol accelerator platform. Again, that network protocol accelerator platform, it's a digital circuit implementation. The Fraunhofer guys, in about 2010, when they started their work, they were eyeing ASIC implementation, but it's pretty generic RTL code, so we can port it to pretty much any FPGA, and we've done so. And the idea is it's a complete TCP, UDP, IP stack. It has address resolution protocol, it has its own MAC, it does IP version 4, it does the control message, it does group messaging for UDP, it has DHCP for client and for server, okay?
Is this a new infrastructure entirely, or you reuse everything that is already there, just software?
So we started engaging with those guys because in a lot of cases the FPGAs don't have a CPU and they need to run TCP because the recipient or the sender expects the opposite side to talk TCP, okay? So it's not a new thing, it's been probably 10 plus years old, but we've been constantly adding to this as a foundation platform for high performance networking. This technology is in production use for years. We use it in automotive engagement, for botnet implementations. We use it in aerospace and defense, where people just want high line rates, high data rates, very short round trip delays, and therefore full acceleration, industrial test and measurement, and more recently telco implementations. And what our idea now is to take the Homa protocol as a message-based protocol without the kind of the tail end latency side effects of TCP, and implement kind of a Homa engine into this existing network protocol platform. Homa is IP version 4 based or IP based, so we can reuse a lot of this thing, and we basically foresee a flavor of the Homa protocol which we call Quad RP as in reliable rapid request response protocol, because when we do a hardware implementation, we need a flavor of the Homa protocol, and we want to distinguish this implementation from the Homa implementation. Okay, and the idea now is to look at applications where normally you would use TCP, possibly TCP acceleration, and look at whether Homa is applicable and useful to this. And because I'm at a storage developers conference, our pitch, our idea is, why not use it for NVMe over Fabric, right? The much that we understand about NVMe, it's message-based, right? You got these PCI Express posted writes. That's not a stream within the other posted writes. It's an individual, it's an atomic thing. Versus a read, you get a completion and you get your data back, okay? That's a flavor of a message, okay? And we understand that in these storage area networks, the network is very quickly the burden. We see and use SSDs which have PCI Express 5.0, 32 gigatransfers per second, 4 lanes. Very quickly, one SSD saturates a 100 gig network. Okay, so the idea is, well, if the network's a bottleneck again, let's make sure it's the protocol to transport this makes efficient use of the network, and at the same time takes care of tail end latencies, which in a distributed storage system we believe has similar positive or negative effects when you have tail end latency than in our real-time control embedded system. Here's a list of references that go into great detail of the Homa protocol. The top one is basically John's rather provocative paper. Let's replace TCP, I think, is a short version of this. His presentation at Usenix about 2 years ago, where he presented his open source Linux kernel module implementation, all the way down to one of his PhD students' thesis, going into like hundreds of pages of the network simulation and the results. Thank you so much. Any questions?
So do you know any NIC vendors who's offloading the message distribution across the CPU?
So, I mean, like, his PhD student ended up at Google. Okay, so no. So question was, do we know of anybody who's been offloading the Homa protocol? No, we don't. I mean, like, the implementation of the Homa protocol became available about a year ago in GitHub when John started the second round of his implementation of the Homa protocol itself. Okay, he added tons of bells and whistles to make it efficient in a multi-core Linux environment, dealing with a general receive offload. Okay, but so far it looks like we're the only ones at this moment who have an interest in turning this into an accelerator for our own use, for our own distributed systems of systems.
So, in case of packet drops, right? Like if you're doing a message-based recovery, if the message is too large, are you going to retransmit the entire message?
Well, a message, similar as in TCP, a message is segmented. You can segment a message. You're not sending as this like 4 gigabyte chunk if you want to transport a database. It's chunked, okay? And it's I think the way the current implementation does it in software, it uses the general segmentation offload in the Linux network API or NAPI, new API, not network API, for GSO. So there's segmentation involved, so you don't miss the entire message and you don't have to do this, but you basically reassemble that chunk again. Yes?
So maybe 2 questions in one. Is it based on IP or UDP or which level of stuff? And a related question, does it benefit from all the goodness that comes with TCP, like the security protocols that are encryption and all that, right?
So Homa is IP based. So it sits on top of the IP layer in the Linux kernel implementation. And yes, one of the things that is a necessity to us is MACsec for privacy and security. So that's totally orthogonal. And what we're actually looking for is there's an implementation from some academics in Spain, I guess, who put a security layer, an encryption layer on top of the Homa protocol. So it could benefit from that. Think of this as TCP, UDP, Homa, okay, not just TCP or UDP.
Actually, I have two questions that build on both of those. So one is there some sort of acknowledgement approach aside from getting the response RPC? Like if you have more unpredictable large network, you might get packet drops because things are routed along different paths. Is there a way for the sender to directly tell that everything is received, or it has to wait for a response?
So the question is with regards to reliability, so is there a way to tell the sender that you haven't received data? Yes, that's part of the Homa protocol. The recipient pretty much expects things, and there's flow control in there, there's counters in there. So at message level, these segments will need to be ordered, obviously, right? But it's not all messages over one stream get ordered, but it's per individual message. So that level of reliability exists.
And then one other question, so that's what it was built on. You said it's built on top of IP. I know there's another protocol, I've heard of QUIC, quick, is similar, sort of having multiple streams for reliable transmission, an alternative to TCP. That's built on top of UDP for the ease of routing. Have you considered whether this would be a problem routing in a large network that doesn't want to send traffic that's not sent over TCP?
I wish John would be here. He could give you a better answer to this one. But the way we see this, I mean, we looked at the QUIC protocol, the Google version as well as the IETF version as a means for us to communicate systems. And from what we understand about the Homa protocol, it's different. Okay, it's really message-based, and it's inherent in the protocol is reliability versus at application level.
I just wanted to add to that. I think, given the reason that you stated and the fact that how congestion control seems to operate at Homa, it seems like it would not be suited well to operate over the internet, and that's strictly implied for data centers.
Yes, yes, I can elaborate on this because we asked John the same question. How about using this for internet, like worldwide connectivity? And now this is really meant for data center where you have a LAN, not for WAN implementation. And that QUIC has been optimized for WAN, correct?
So the QUIC addresses, so in testing mode, obviously QUIC can be done without encryption. And there was performance data, because of the head-of-line blocking and the congestion control, even on fast, short networks, QUIC had better performance than TCP. So I'd be kind of curious to compare those same numbers with unencrypted QUIC. Obviously that's not what Google uses and all that, but you can do it for testing. It wasn't the primary use case of QUIC, but it's interesting. What I was mainly interested in as a kernel maintainer, though, is what was the feedback from the Linux kernel network guys, because from my perspective, all I care about is there's a socket API-ish kind of thing. I mean, we literally don't care. We just want that API. And as you know, last week, the socket API just changed in Linux kernel, so your code wouldn't work. So I guess what I'm getting at is, like, what's the feedback from the Linux networking guys about putting in experimental modules? You can try it.
Quite frankly, this is the strongest pushback to whoever we talk to about, how about have a look at this Homa thing. It's like, well, it's not API compatible. Don't make me change my Linux APIs, okay? That's quite frankly, we're looking at applications in our distributed systems of systems, which is message-based, which are RPC-based, MPI-based, those kind of implementations, as well as we believe in NVMe over Fabric implementations where you don't have to have a TCP socket interface because it's been dealt with by the SmartNICs, by the host bus adapters anyhow, right? So no exposure to the Linux software world, because we know one thing by now, software isn't soft anymore. If in order to change something, it undergoes so much scrutiny, so much testing in order to deliver the same quality of results these days than it was before. So that's the biggest pushback we see. It's not API compatible. I'm not interested in rewriting the API for all my software.
I mean, what's strange about that is, like, take an example. Sunday over quick. All we care about is something that looks kind of like a create of a socket, something that kind of looks like I'll give you an IPv4 IPv6 address, and you'll take that address, a connect of sorts. I think that's maybe the one that just changed in the Linux kernel. It's trivial. And then after that, I'm just doing write and read. So if you have a read and a write and something that vaguely looks like a connect to an IP address, I mean, we're talking 10 lines of code. This isn't a big thing. But if you're talking about a totally different model, everything changes.
Yes, absolutely agree. I mean, like we've seen the push for user space network protocol handling, right? DPDK, SPDK, and all of a sudden the Linux kernel went on par with this one. So there's a competition. But again, I think what we heard earlier today as a question, our focus is on LAN, not on WAN. And I think that's fair to distinguish here. Any more questions? Well, thanks for that. I started with a provocative question, and I hope by now we all know it's not bad, TCP. I mean, like next year it's the 50th anniversary, right? And then half of us weren't really born then. Thank you.